Superfluidity was first observed in cold atom systems, and it can be associated with a Goldstone mode originating from spontaneous symmetry breaking, which occurs at very low energy, so at very low temperature. So we first need to investigate the spontaneous symmetry breaking mechanism in this Lagrangian, and then we will integrate out all the high energy mode in order to isolate the Goldstone mode, which characterizes the low energy physics of the system. The potential for this Lagrangian can be expressed as: we now plot this potential as function of the real and imaginary part of the field. We see that the minimum for this potential is obtained for non-zero value of the field, and we therefore recognize a spontaneous symmetry breaking mechanism. Recall that the spontaneous symmetry breaking mechanism occurs when the Lagrangian exhibits a symmetry, but not its vacuum. And the associated symmetry here is a global gauge invariant. We indeed see that the Lagrangian is global gauge invariant. So the Lagrangian is global gauge invariant. But to see if the ground state is global gauge invariant, we first need to see how the A and A dagger transform. So we see that A transforms like phi. Similarly, we can transform a state with n particles. So the ground state, which has a fixed number of particles thanks to the chemical potential, is not invariant under gauge transformation because it has n particles and acquire a phase when the gauge transformation is applied to it. This is a typical situation of spontaneous symmetry breaking, where the Lagrangian is unchanged under transformation but not a ground state. So now we do what we did in the particle physics context. We choose one ground state, one vacuum, and we expand the field and then the Lagrangian around this vacuum. So we have two modes. We have the possibility to roll along the gutter or to climb the wall. So as before, we choose a ground state along the real axis for convenience. We call theta the Goldstone mode, the mode which corresponds to rolling along the gutter and which costs little energy, so it's a low energy mode, and that's because it is massless. And we call H the Higgs mode, which corresponds to climbing up the wall, and that's a high energy mode because it has definitely a finite mass, so it costs energy to move the field out of the vacuum. With this parameterization, we see that Goldstone mode corresponds to a gauge transformation of the field. Indeed, it only changes the phase of the field. However, the Higgs mode corresponds to a change of the norm of the field. Indeed, the modulus of phi can be written as a square root of phi dagger phi. And phi dagger phi corresponds to the density in X, and in the ground state, this is just the density n. But the Higgs mode takes us outside of the ground state. So we can use this expansion of the field around the ground state to rewrite the Lagrangian. The first term leads to a sum of two terms, and one of them is a total derivative, which we don't care of because the action is a time integral of the Lagrangian, and we assume our field to be zero at infinity in space-time. And similarly, we are going to disregard all total derivatives from our Lagrangian. N is just a constant, so again this term is a total derivative which we can disregard. In addition, it will be enough to only keep the fields in second order in theta and in H, or in their product. Therefore, the terms in H squared theta dot is the third order, and we can disregard it. The second term can be expanded in the same way. Keeping only second order in the field, we see that the square root of n is the only term which is going to contribute here. For future convenience, we rewrite this term using the fact that total derivatives do not contribute. Finally, we are left with the interaction and the chemical potential terms, which we can rewrite. The second term is irrelevant because it is just a constant. As we only keep the second order, the h squared term doesn't contribute. We finally get the Lagrangian. Our next step is to quantize, and we will do that using many-path formulation instead of canonical quantization, because that will allow us to integrate out the high energy mode, which is Higgs mode, more efficiently.